So this chapter has focused on dark matter and kind of hinted at dark energy. And actually dark matter, the presence of dark matter, is important in our overall understanding of what we call the Big Bang Theory. The fact that our universe began unfolding space and time some 13.6, 13.7 billion years ago. And so when we look at kind of back in time to the time of what we call the Big Bang, actually the amount of matter present at that time, dark matter, energy, and regular matter and regular energy, actually is kind of key in understanding, will our universe continue to expand? And if it expands, will that expansion continue to accelerate? And so I'm not going to play this little animation for you, but one of the things we talked about was that if you throw a ball straight up in the air, right, you know that that ball is going to come back down, and that's what this animation would show you. But if we throw that ball, I think it's like 11.2 kilometers per second. If we throw that ball fast enough, okay, that ball will escape the mass that's creating gravity on that ball, the mass of the Earth. Okay, we escape the gravitational influence of the mass of the Earth. And so we kind of liken that to the matter and energy that was all kind of in a ball at the time of the Big Bang. So how much matter and energy there was will kind of dictate what our ultimate fate of our universe will be. So I think this is kind of a neat sort of slide. The way this works is down here we see the Big Bang, okay, and kind of the way this kind of arcs out, that's showing you expansion. And so that would be in the past, the Big Bang. The present is this little orange line, that's us today. And so literally, if there was a whole lot of dark matter, lots and lots of dark matter, that was part of what we call a kind of a singularity, the point that unfolded and created our universe. If there was a lot of matter, what would happen is kind of like that ball falling back down. In the fact that we can go ahead, we can have this expansion, but at some point you can see here in the future, the expansion is going to stop and it's going to begin contracting. And so some would say then with this scenario, we are kind of in store for us at some time in the future, we're going to have a big crunch. This is an example of a recollapsing universe. And this scenario works if the initial amount of dark matter and energy in our universe was lots and lots and lots. Okay, so here's another scenario. Let's say we had what we call just right amount of matter, mass, and energy as our universe at the time of the Big Bang. Okay, so here's the Big Bang. We have the universe is expanding. And then what happens then is the expansion kind of levels out, it stops expanding, and we have a particular size. It'll stop expanding, it just kind of will coast, okay? And that's with just the right amount of mass, matter, and energy. Well, if we go with about 25% of the amount of matter required to meet what we call critical density, if we have a little less matter than that, we can end up with an expanding universe that will expand uniformly like forever. And I used the word coasting a minute ago, but this would be the coasting universe, where it continues to accelerate. Or not, I'm sorry, it continues to expand, but the expansion is not increasing, so it's not accelerating. Okay? So that's a different scenario. Notice that in each one of these scenarios, we can kind of, from our present time, go back to the Big Bang. And the Big Bang is, for instance, for the recollapsing universe, it didn't happen as long ago. For the critical universe, it happened longer ago. And for the coasting universe, it happened even longer ago. Does that make sense? I think this is a really good slide, really good figure. Well, again, we know that our universe, not only is it expanding, getting larger, but our universe, the expansion itself is increasing. So that's a type of acceleration. And so one of the things that, one of the fundamental laws of motion that Newton came up with is this: there is some sort of acceleration like this. It must be funded by some sort of force. It must be driven by some sort of force, some sort of energy. And what is that what is that energy that's driving the acceleration of our universe, the accelerated expansion of our universe? That would be dark energy. So this is yet a fourth scenario. And this is most similar to the last scenario where I showed like 25% of the critical mass as being the original mass associated with our universe before it began unfolding space and time. So these are just kind of links to remind me to tell you to take a look at the playlist, the YouTube videos associated with this subject. Just awesome. So this is kind of highlighting one of the things I told you, is that based upon these different scenarios of our universe, the big crunch was the recollapsing universe, or the critical amount of matter, just saying that at some time it's going to stop expanding, or the 25% of the mass, and we end up, or something less, I guess I should say mass, initial mass, something less than critical mass. It would continue to expand, but that expansion isn't accelerating. And here we have an accelerating universe, which in this case, we go back, extrapolating, using our model to go forward and backward. We go back to even the latest, the longest ago, the initial, what we call the Big Bang. So, again, to me, this seems like we're kind of going back a little bit, but one of the things we said that we can use supernova type 1A events in distant galaxies as candles to know what sort of recessional velocity those galaxies have, or I should say actually just what sort of movement those galaxies have in our universe. And so what we find is, and actually this is proof of the ever accelerating expansion of the universe. And if we take those data and associated with to give us the motion of those galaxies, and if we plot that on a chart here, what you're looking at are the 4 different scenarios of our universe. There's the recollapsing or the big crunch universe. There's the critical universe, and each one of these these scenarios depend upon the amount of matter initially present at the Big Bang, amount of matter, mass, and energy. So notice that here this orange line is an accelerating universe, and so the movement of the galaxies that these supernova type 1A events were observed in actually lie best along this particular scenario, an accelerating universe. So we'll talk more about the Big Bang theory in chapter 17.